So in the previous video we talked about what the Biot-Savart Law is. Now we're going to come back and talk about basically how you can use it to figure out the magnetic field. And we'll do this in terms of sort of the two most common cases that we'll sort of deal with. So we said again, the Biot-Savart Law tells us that the contribution to the magnetic field due to some tiny little current element IDL is given by this expression. And we said that this expression, what we're going to do is we're basically going to think about its magnitude. And again, we'll use a right-hand rule to determine the direction. And the way that this will work out is, again, because of our cross products, basically we'll end up with everything pointing in the same direction in terms of the magnetic field contribution, so that we'll pretty much end up with a one-dimensional integral where what we need to figure out are dl sine phi and r squared. So the process that we're going to do is we'll draw a sketch, we'll pick a current element, we'll draw in r hat. So again, r hat is the unit vector that points from your current element towards the point P. We'll use a right-hand rule to determine the direction of dB. And then we'll figure out what these three terms are that we need. We'll plug them into the magnitude, and then we'll go and integrate from our initial point to our final point. So in terms of the first example, let's just take a magnetic current, or the magnetic field due to a current carrying arc of wire. So we're just talking about some circular stretch of wire. Here I happen to have drawn it sort of halfway around the circle, but there's nothing sacred about the halfway around the circle part. And in fact, what we'll see is we're going to do this in general so that it doesn't matter whether this is halfway, all the way, a quarter of the way, just some tiny fraction of the way. Just as long as what you've got is a wire that's been arranged, a current carrying wire that's been arranged along a circle, and then point P, where you're interested in the magnetic field, is basically sitting at the center of that circle that the current is going around. So in this case, so here's our drawing. We're going to pick a little element IDL. I'm going to draw in, there's R. So R hat has to lie along R and point in the direction towards P, so from my current element towards P. And then this lets me figure out what phi is. And so your temptation at this point might be to say, well, wait a second, you happen to pick right in the middle of this, didn't you pick a special point? And the one thing that we'll sort of emphasize as we come back to this is you could pick any point along this circle, and it doesn't matter. Your distance r is always going to be the radius, and these two vectors, r hat and IDL, are always going to be perpendicular to each other. So even though it looks like this might be a special point in this case, there's actually nothing special about it. That these values are going to be the same for any point that we would pick. So here's dB, and what I need to figure out now are the dl, sine phi, and r terms. So dl, since I'm going around a circle, again what we've said is dl is basically telling you what do you need to integrate along. So that's usually going to be either dx, because we've got a line in the x direction, dy, because we've got a line in the y direction, or we're integrating around a circle. So here we're integrating around a circle, so we've got r d theta. Sine phi, well, let's do r first. So again, r is just the distance from your current carrying element to the point P, and again, at any point you picked along this circular arc, that was always going to be the radius. And then sine phi, well, again, we've said that in this case, phi happens to be 90 degrees. So these two vectors are perpendicular to each other, and they would be perpendicular at any point you picked. And so sine phi here is 1. So when we go and plug this all into our expression for dB, again, here's the mu naught over 4 pi term, there's I, there's my dl, r d theta, here's my r, right? Little r is my big R, radius squared, and then I haven't even bothered to write the sine phi term because it's just equal to 1. So I simplify this and basically get this expression, and so this is what I want to go integrate. So when I go to integrate that, well, I'm just going to do the integral again. We're going to keep this sort of appropriate sort of in its most general form. So this is appropriate for kind of any length of arc that you happen to be going around, because we're just going to integrate from some initial angular position to some final angular position. When I plug in dB, what I see is okay, I get the mu naught over 4 pi, that's just a constant. The I, well, we're going to treat that as a constant because I'm not letting my current change at this point. R, again, that's just the radius of the circle, that's a constant. So all of this we can just drag out of the integral, and the only thing we're left with is the integral from some initial angular position to some final angular position of d theta. And we know that this is just going to give us delta theta. So here's the expression we get for basically the magnetic field at point P along any length of arc you want. The only thing you've got to do is sort of come back and plug in whatever the length is. So the case we'll use this in most often is dealing with the situation where we've got a magnetic field around a current carrying loop, so a full circle. And so we can take our expression and just, if we've got a full circle, then delta theta happens to just be 2 pi. So when we go plug in our 2 pi, you see, well, if I've got 2 pi up here and 4 pi down there, that's going to cancel the pi's and just leave me with a 2 on bottom. And so the magnetic field at the center of a circular loop of radius r is given by this expression, mu naught I over 2r. And so this is sort of the most common case that we'll deal with, our magnetic field due to a current carrying circular wire. Now let's look at a second example. So how about a magnetic field due to a finite current carrying wire of length L at a point P, a distance A away from the wire, along its bisector. So we'll make our life a little bit simple here, and we'll let point B be along the bisector of our current carrying wire, so that half of the length of the wire is over here and half of the length of the wire is over there. Again, just pick some point. I happen to pick this one. There's r hat, or there's r, and so there's r hat pointing back towards P, and so here's my angle phi. So when I go to figure out the pieces I need for dB, well, in this case, basically, since my wire is running up and down, I'll choose to call dl dy. R squared is just going to be this distance squared plus this distance squared, take the square root, or R squared is just going to be this distance squared plus this distance squared from Pythagorean theorem. So basically what I'm doing is I'm letting this be the x-axis, this be the y-axis. So basically the position of my current element happens to be at y. So this is y squared, this is a squared. And then sine phi, well, this angle here is actually phi. But the sine of this angle happens to be the same as the sine of 180 minus phi, same as the sine of this angle. And the sine of this angle I can see is going to be the opposite side, a, over the hypotenuse r. So a over r, in terms of what we've already figured out, is just going to be a over the square root of a squared plus y squared. So here are the three pieces that I need to go plug into dB. And so when I do that, there's my mu naught over 4 pi, there's I, now I've got dy over a squared plus y squared, times my sine term is going to have a over the square root of a squared plus y squared. And again, I just simplify this down, so I've got mu naught over 4 pi, I, a, dy over a squared plus y squared to the 3 halves. So this is the expression that I now want to go integrate. Again, given sort of the way that I've kind of set up this problem, I'm going to integrate from negative L over 2 to L over 2 in terms of what's going on in y. And so when I plug in this expression, mu naught's a constant, 4 pi is a constant, the current's going to be constant, and a is just some distance that we're holding fixed. So these things I can all pull out, but the dy term is going to stay in, that's my variable of integration, and then this term includes my variable of integration, so I can't pull it out. So I'm left with mu naught IA over 4 pi that I've pulled out, and then my integral from negative L over 2 to L over 2 of dy, my variable of integration, over a squared plus y squared to the 3 halves. And this is this is an integral that's in the table of integrals in your textbook. This is one that basically we can go look up. We'll go look up what the antiderivative is from the integral. We evaluate it at the endpoints, and this is the expression that we get. So for a finite length of wire, this is what the answer is going to be for the magnitude at some distance a away from the wire along the bisector. So we are throwing in that extra caveat that I can't be talking about a point over here or a point over there. Well, the most common wire that we're going to deal with in terms of working through some of these problems is just letting our wire be infinitely long. And so in the case that our wire is infinitely long, basically what happens is this term, when I evaluate this term in the limit as L goes to infinity, what I end up with is this expression. So basically, this is going to give me a factor of 2 when I take its limit as L approaches infinity. That 2 is going to cancel with the 4 down here to leave me a 2 pi on the bottom. And all we've done is change our label for what we're calling the distance we are away from the wire. And we'll see that the reason that is because basically the magnetic field is going to circle around a long straight wire. And so whatever point you're interested in, this sort of becomes the radius of the circle when you're a distance, the radius of the circle that the magnetic field goes around when you're a distance, some distance r away. So this will be the expression that we'll use most often in dealing with our long straight wires. Now, one thing to make sure is clear. Notice that this expression is incredibly close to the expression for our circular loop. The difference is there's a pi here, there isn't, and there's a pi with the infinitely long wire, there isn't a pi when we're talking about the circular loop. Otherwise, they're basically exactly the same. So that's just something to keep in mind. Again, just sort of trying to make sure you've got the right expression when you're plugging in to solve for the magnitude of the magnetic field due to either a circular loop or an infinitely long wire. So with as with any other problem, now what we're going to be able to do is we've basically used our Biot-Savart Law to figure out what the expression is for a single element, and now as we start bringing up multiple wires or multiple circular loops, now we just use superposition to add up the field contributions from each of those multiple wires or multiple loops to figure out what the net magnetic field is. So hopefully this problem seems very familiar because, again, we've sort of done this before in terms of using either an integral or Gauss's law to figure out what the electric field was due to some particular type of charge distribution, and now we bring multiple of those charge distributions up and we can just add up those contributions using superposition. We're going to do exactly the same sort of thing for the magnetic field. We've used the Biot-Savart Law to get our most common, an expression for the most common contributions that we're going to use. So some circular arc, some infinitely long wire, and so now we're just going to come back and add those together as add those together using superposition to get the net magnetic field at point P.